This is Grand Admiral Rosine, following the physics directive to explain conceptual modern physics. If you do not know what proper time is, I would suggest watching part 1 to this video. You can find the link in the description. Now, we will explore the meaning of simultaneity in general relativity. According to general relativity, there are infinitely many possible spacetime curvatures, and each curvature offers a unique definition of what objects are accelerating. For this reason, acceleration can be considered relative according to the shape of your local patch of spacetime. But if acceleration is defined in infinitely many different ways, simultaneity breaks down. You can no longer define which objects change simultaneity, so you can't define simultaneity at all. In fact, without simultaneity, you can't define a global coordinate system, not even one that allows for disagreements between different reference frames. To be clear, nothing crazy happens from the speed of light's constancy, causing disagreements in its motion between space-time curvatures. The speed of light can actually differ between coordinate systems. It is only constant locally, so within its local space-time curvature. Without simultaneity, all space-like events become irrelevant. In general relativity, all that matters are light-like and time-like events, since those are the only events that can affect or be affected by you anyway. Now, this easily raises the question, why couldn't you use the speed of light to calculate what light-like events used to be space-like and simultaneous? You absolutely could. The key thing is that you would only be finding what was simultaneous to you according to your local space-time curvature. The relativity of simultaneity and all of its effects in special relativity do not become unusable in general relativity. They just describe a very unique case in which space-time is perfectly flat, hence why it's called special relativity. Special relativity still works perfectly in constant space-time curvature. So, if you define a coordinate system according to your local space-time curvature, you can also define simultaneity within that coordinate system. Different curvatures will still disagree on simultaneity, and you will be unable to compare how you define it. But if simultaneity can't be confirmed, how do you determine that start and end points of two objects' world lines to calculate their proper times? You could do so in a set coordinate system, but it would be ineffective at describing what both objects experience. To find a start and an end, you must find 2 points on the object's world lines in which they experience the same spacetime curvature. Usually, these will be points in which they share the same position, making things easy. But if they are in separate positions, you can still define simultaneity according to their relative motions within their identical local spacetime curvatures. Then, to calculate proper time, you just find the amount experienced on both world lines in between the start and end points. Accelerations will not necessarily be defined according to the spacetime curvature they agree on, but instead each object's proper acceleration, which only happens when an object defies its geodesic. Since proper time is the method through which we calculate time, instead of relying on the relativity of simultaneity alone, general relativity is able to function without any concept of simultaneity. Simultaneity is a useful tool in ideal situations where space-time curvature is constant, but it is irrelevant when considering more general situations. If you enjoyed this video, please give it a like. If you wish to further explore conceptual modern physics, subscribe to my channel and join me in the Physics Directive. Long live the Empire!